My name is John Knoeller, but everybody calls me TJ. Get a couple of beers in me and I'll tell you why. I'm here to talk to you about the way GPUs look to HTCondor and the bits of big changes in the what we call the 9X releases. That's 9.1 and later. In particular, some really big changes in 9.8, which is now out and available for you to play with. Hello. There we go. All right, so when we decided to add GPUs to Condor, we did this by adding what we call custom resources. Like all execute nodes are going to have CPUs and memory and disk and are going to need to allocate portions of that to the job. But not all execute nodes are going to have GPUs. And we wanted to solve this problem in a way that would allow administrators to make new kinds of custom resources beyond just GPUs. And so what we did was we added a couple of configuration knobs, one for custom resources that are just a quantity like memory, where you just need to specify how much of that exists. And the other one, the more interesting one, where the custom resource is a set of identifiers. You use this by using the knob machine resource inventory underscore, and then you come up with a tag that represents the type of custom resource. In this case, we've decided that the tag we will use for GPUs is GPUs. I will be consistent about capitalizing GPU and doing lowercase s, but in fact, this is case insensitive everywhere. Then we also wrote a little program, Condor GPU Discovery, that is meant to be run by this machine resource inventory knob. And it spits out information about the GPUs that it discovers. And part of the reason we do this outside of the startd by running a special program is because we have to find and then load the NVIDIA libraries, or if they don't exist, some other set of libraries. OpenCL is the other thing we support right now. And we don't want to hang the startd if that hangs. I mean, NVIDIA libraries do sometimes hang. GPUs are temperature sensitive, shall we say. So this is the original output of Condor GPU Discovery. When we first did it, it spits out this one required attribute here, detected, and whatever that tag is, GPUs in this case, and then a list of identifiers. And then everything else it spits out needs to be class add attributes that describe or properties of the resource being detected. In this case, the GPU capability is a number that NVIDIA has defined, device name, the global memory. All of this is information we get by querying the originally the CUDA libraries. More recently, we use the driver library because the CUDA libraries are not necessarily in the path most of the time these days. Then what happens is the execute node, the startd, after it runs discovery on startup, it takes that detected GPUs attribute, it saves it off, it counts the number of things in that string, and it decides that's how many GPUs it has. And then when it creates a slot, it will assign 0 or more GPUs to that slot, and will publish the identifiers of those GPUs in an attribute called assigned GPUs. For static slots, this is typically 1. For partitionable slots, it's typically all of the GPUs. And then for dynamic slots, it'll be one of the GPUs that are part of the static or the partitionable slot. All the other attributes in discovery output are just published in all of the slot adds. Now this turns out to be a problem for heterogeneous GPUs, and we'll get back to that later. Now that thing I just showed you, that was the original output of GPU discovery. Back when NVIDIA expected you to identify what GPU you were going to use by passing it a number. You would say, I want to use GPU 1, And so we gave them identifiers CUDA1, CUDA0, and so on and so forth. That turns out not to be stable. If a GPU fails, sometimes the NVIDIA driver just moves the other IDs over, so that now what used to be GPU1 when we booted the machine shows up as GPU0 sometime later. And this is a problem for the StartD, because the StartD only does discovery on startup, right? The bag of resources available to hand out to jobs is something you must tell the StartD when it starts up, and then it's not allowed to change as the StartD is running. So starting with HTCondor 9.0, we switched to using a new scheme that NVIDIA has now supports, where they give each GPU a UUID, a unique identifier. It's a 128-bit random number. It turns out that the first 32 bits of that is sufficiently unique and allowed by NVIDIA as the GPU identifier. And so that's what we use. We use the argument short UUID by default to discovery that says, spit out these IDs that are the first part of the number. So this is what discovery looks like in HTCondor 9.0 with this short UUID output. Now the detected GPUs are GPU and some random number, GPU and some random number. For the attributes that are common to all of the GPUs, we can still give them an attribute name that represents everything. So capability, both of these have the same capability value. For attributes that are different between the various GPUs, we take this GPU identifier, we clean it so that it can be used as a valid attribute reference. Basically, we replace the dash with an underscore, and then use that as a prefix on, use that as a prefix on the attribute name. So GPU, UUID, and so on and so forth. Properties that vary by GPU, therefore, have attribute names in the StartD that you cannot predict from outside the execute node, and that is somewhat problematic. If it turns out things like your capability number vary by GPU. And here's a good example of that. So here's a machine that we have that has two different kinds of NVIDIA GPUs. It still has stable GPU identifiers, but the only attribute that is common to these is the CUDA max supported version, which is actually about the driver library and not actually about the GPU at all. In this case, we have GPU device names. One of them is Titan, the other one is Tesla. It is difficult for a job to match on these attributes because the job isn't going to know what GPU ID prefix to use unless you're working in a very small environment where you just have a few execute nodes and your users can go discover what's available before they even write their scheme files. So here's the state of the world as of 9.0 release. We support homogeneous GPUs just fine because the attribute names that get published in all of the slot ads are the same, right? You get CUDA device name, and it's the same in every attribute or in every ad. For GPUs that are heterogeneous, however, we publish a whole bunch of different attributes, each of them with variable names, and we don't distinguish between the attributes that talk about the GPU that is assigned to that slot and the attributes that are assigned to other slots. In effect, what you can do in the 9.0 schema is your job can say, I want to match a machine that has a GPU of this type, but not, I want to run on that GPU. And this works just fine when all the GPUs are the same, but it doesn't work at all if you need to land on one of the two available GPUs. first of all, it's hard to write the expression to even match that. But even if you did, when you land, there's no guarantee you're going to run on that GPU. This was the state of the world when we started the 9X series, the 9.1 and the 9.2, and we knew this is something we needed to solve. And what we need to do to solve this problem is we need to give the matchmaker the ability to distinguish between the various GPUs properties while it is matching. And to do that, we need a new format for expressing GPU properties. And we need to stop advertising in the slot the properties of the GPUs that are not assigned to that slot, right? So that's one piece. The start date has to advertise differently. And then the job needs to have a requirements expression that solves two different problems. One is when matching to the machine or the partitionable slot, you have to say, I want to match any machine that has at least the number of GPUs that I need, that have the properties that I need. But then when you match the dynamic slot that gets created, you want an expression that says all of the GPUs in this slot had better be the properties that I need. And that's actually, in the general case, impossible. And so we've decided to do something that was a little simpler than that, but is sufficient. That is, we write an expression which says match the slot whenever sufficient GPUs in the slot match the requirements, properties requirements that I design. And in generally speaking, we arrange so that the D slots have heterogeneous GPUs, or homogeneous GPUs, I'm sorry, even though the partitionable slots may not. All right, so in order to do this, the output of Condor GPU discovery had to change. That's where it all started, was Condor GPU discovery spits out these attributes, but we have no way of knowing which attributes belong to which GPUs. The start D doesn't, the discovery does. So discovery now, and at the moment you have to pass a special argument to make this work. Eventually this will become the default behavior. You pass discovery dash nested, and instead of printing out a bunch of attributes with the properties of the various GPUs, what it does is it prints two nested class adds, or at least two. There's a common nested class add. These are all the attributes that are the same on all, or the properties, I'm sorry, that are the same on all GPUs. And then for each GPU individually, we print a separate nested add with the properties that are specific to that GPU and not in the common list. Okay. When the start D sees this output, when the start D sees nested adds rather than simple attribute value pairs, then it behaves differently. It takes this common add and the GPU specific add, and it merges them together. And internally, it's creating a sort of collection of class adds. You can't see this from outside the start D directly, but it's creating this internal collection of class adds, which is the property add for each GPU. And then what it is doing is adding a new attribute to every slot called AvailableGPUs. This attribute will be a list of references to the individual GPU property adds. And it will publish available GPUs containing only the GPUs that are assigned to that slot and not assigned to a child of that slot. So this is what the start D output looks like if you use nested discovery, right? In this particular example, I'm showing a partitionable slot that is assigned to two GPUs, one of which has already been given to a child slot, and the other is still available for matching. So we see the number of GPUs here is 1, because only one GPU is still available for matchmaking. Total GPUs is 2, because that's how many of the slot was assigned originally. The list of all the assigned GPUs is here in its form, just like it was all along. And then this new attribute, available GPU, keep doing this. available GPUs is a class add list of the names of other attributes. In this case, it's this one here, which is the properties of the GPUs that have not yet been assigned to any dynamic slot, that are still available for matchmaking. All right. And then the only other piece we need is a way, at the time we are binding GPUs into slots, a way of using that GPU property add to control which GPUs get bound. And there's a new mechanism in the StartD for static slots and for partitionable slots, where when you describe the slot resource bag, you do this. Now that you used to have to put all of this on one line. We now support a multi-line form where you say CPUs is this many, memory is this memory, GPUs is 2, and this constraint must be true for every GPU that you assign to this slot. And this constraint is going to be evaluated against the property add of the individual GPUs one at a time while looking for GPUs to assign. All right. Now that works for static slots and partitionable slots, but for dynamic slots, we need that constraint expression to come from the job, not from the StartD config. And so there's also a new mechanism for this, right? When a job wants GPUs, has for all along had an attribute called request GPUs. It's the number of GPUs I want in the job. The job may also now have an attribute called require GPUs. This is an expression which will be evaluated against all of the GPU property adds in the StartD if we use that job to create a dynamic slot. So the first job that lands on a machine that is a partitionable slot, that first job, we look at it and we say, okay, I need to make a slot with 2 GPUs to run this job, and I shall find two GPUs that match this constraint expression. Okay. This does not directly affect matchmaking. It only affects the creation of dynamic slots. However, indirectly, we also use it for matchmaking. So we added 2 new class add functions. The first is just a general mechanism. The function is called eval in each context. The first argument is going to be expression like that, capability greater than 7.5. The second argument is going to be a list of adds like that available GPUs attribute that the StartD is publishing. What this does is return a list containing the evaluation results of each of those adds using that expression. And so you would get back true, false, true, or so on and so forth in the typical case. But you can also use this in a a general mechanism, right? You can do condor status -af, eval in each context, device name, comma, available GPUs. And what you'll get back is an array containing all of the available device names. Okay. Now, the other thing we did is a variant on this function that is more specialized called count matches. And this is equivalent to essentially that first function passed to the sum function. We want to know how many times when we evaluated that expression against each of the adds did we get the result true. And if that number is at least as many as request GPUs, then that constitutes a match. Then we also added to the submit language a new keyword. This keyword is require GPUs, and it does 2 things. One, it just takes whatever you pass it and publishes it in this require GPUs attribute, job attribute. And then it also modifies the requirements expression of the job. So without require GPUs, the requirements expression of the job that wants GPUs is going to look like this. It's going to say target.gpus, that is the startD's number of available GPUs, greater than the number of requested GPUs. That's the case where the job doesn't care what kind of GPUs it gets. It only cares how many. If you care what kind, then you add this keyword required GPUs, and now the requirements expression is count matches of my required GPUs against target's available GPUs, and that quantity has to be greater than or equal to the request GPU. So that solves our matchmaking problem. All right. So now we can match individual GPUs. However, think about all the things we had to change. The startD has to publish different attributes. That at least fits within the allowed schema. But nonetheless, the startD has to be version 9.8 or later in order to support this GPU discovery nested advertising. Then we added a new class add function. That's going to get evaluated in the central manager, in the matchmaker. It's going to get evaluated in the startD in order to make sure that the job's going to match. And it's also going to get evaluated in the access point. The sched-D will not send a job to a partitionable slot until it has already verified that it fits within that partitionable slot. And so you have to upgrade your entire pool to use this new class add function. All right. Questions? This is not the end of the talk, but this is the meat. This is all the new stuff. So any questions here? Yes.
Yes, we have one online from Matthew West. We're going to ask you to unmute.
Oh, I might be jumping the gun that's on this from what Christina said, but I was just curious, are we going to get to splicing GPUs into individual GPUs into subpartitions? Because some workloads don't necessarily need, a full fat A100 for, individual processing.
Yes, Matthew, there's some discussion of this in the remainder of this talk.
Okay, all right, that's fine.
So just big picture, if I'm only a user and I never look at the raw requirements of the class add, I need to know how to use the required GPUs, and I need to know my sysadmin has upgraded the cluster, but then all the class add details kind of at the user level are forgettable, right? Or is there something that users need to understand with the new class add functions?
It's something that in order to write a required GPUs statement in your submit file, you're going to have to know what properties are available from GPUs. That's something that pool administrator can just publish. The set of properties comes essentially directly from NVIDIA. It's pretty standard. There's like 6 of them, of which capability and device name are the ones that we've seen people using. And global memory is the other one, the memory of the GPU.
We have a question from Douglas Benjamin. We're going to ask you to unmute.
So you mentioned memory. So how many things can you sort of tag together? Because a user might want compute capacity, more than just compute capacity, or more than just memory. They might want them both.
Oh, yes, I showed only simple constraint expressions because those fit on my slide. But this is just like any other requirements expression. I can say capability greater than 7 and device name equals, or memory greater than, it can be arbitrarily complex, the expression. Of course, the set of available attributes that you can look at amounts to about 5 or 6, maybe as many as 10 in the largest case. So you can't get too crazy.
No, I understand, but if we have to publish something to our users, then we need to say, okay, here, this is what you can put in if you need more than this amount of memory or.
Yeah, you could do that. An example with 2 clauses in the expression might be worthwhile, just to show that that's possible. Do you use quotes? No, this is an expression. It has to be treated as an expression. Do not put it in quotes or it will not work correctly.
Will you be, is there any future plan to support the AMD GPUs with the
I
Condor?
can't quite hear you. I'm sorry.
Sorry. Is there any plan to support the AMD GPUs with the Condor GPU discovery tool?
We already support the AMD GPUs with the discovery tool. The set of properties we get back from AMD GPUs, this is OpenCL is the library they use. The set of properties is different, but it does work. Right now, if we detect NVIDIA GPUs, we don't look for any others because OpenCL will re-report the NVIDIA GPUs using OpenCL, and that gets confusing.
Okay, that's good to know because we have a cluster with mixed types of GPUs that usually people can choose which one.
Are they
want
mixed on a single machine?
on a single? Sorry.
Do you have a single machine that has both AMD? Oh, then it won't be that big a deal. It's a little hard to write the expressions when you have 2 different names for the same thing, but it's still possible to do. You just have to start using if undefined this, then match that. It's doable.
You answered my question in part.
Okay.
I guess, so to be clear, you support what OpenCL support reports, but not anything that's AMD specific properties, right?
I once again couldn't hear.
Okay. Sorry, so for AMD GPUs, we will report things that OpenCL reports, but anything that's like specific AMD drivers, we do not currently.
That's
detect.
correct. The names of the attributes just come from the library that we're querying. We don't really have, I mean, we do control it, right? We actually give them names, but the names we give them are based on the APIs that we call to get the information back. All right, more, or shall we move on?
So I often use Condor Q-better to find out why my jobs did or did not match. How will that, has that taken these new GPU differentiation?
So Condor Q-analyze is unable to dive into functions. It will show you that the function returned some quantity and that quantity was insufficient, but it doesn't actually know how to dive in and analyze the individual GPU property bags. You'd have to do that in a different way. So yeah, right now that may be a limitation, although generally speaking, the quantity is going to be good enough, I think. All right, let us move forward. Okay, so this is a capability we've had for a little while, the ability to take a GPU offline. This is a configuration. Basically, you add to the start config. Yes, I know you detected this GPU, but do not match jobs to it. You just specify offline GPUs and the names of the GPUs you want to be offline. The new improvement here is that offline GPUs can be made offline with a reconfig. It does not require a restart of the SCED, of the execute node. However, you cannot change the resource bag of a slot while the start D is alive. And so typically taking GPUs offline would mean that new dynamic slots could not use them, but that static slots could still use them, and partitionable slots would still advertise that they existed. Now, taking a GPU offline removes it from the available GPUs list. And so you can't match make against an offline GPU, even if it is still advertised as a GPU assigned to the slot. So that is an improvement over the status quo. There was a question about GPU sharing. We've had GPU sharing for a long time in a completely unsafe way. That is, you could write a wrapper script around discovery, and for every GPU that discovery discovered, you could duplicate it. And so it could say, I have CUDA 0 and CUDA 0 and CUDA 0 and CUDA 0. And what that would mean is 4 jobs could land and all run on CUDA 0, all run on that device. In 9.0, we made this first class. So you can now pass an argument to discovery that says, go ahead and advertise for every GPU you find, advertise its name more than once. You can also use the divide argument that says advertise its name more than once, but also alter the memory advertised so that it is divided by the number of GPUs you average. This isn't particularly safe in the sense that there's no way of ensuring that the 2 jobs that land on this GPU don't each try to use all of the memory the GPU has, that they stick themselves within the limit that they requested. But it does solve the problem for pools that have well-behaved jobs and administrators who can, kind of keep track of what's going on. Upcoming work that we are working on right now, but not ready to show you, is a better way to do this. So we're going to change the P-slot claiming protocol. I'm getting down in the weeds here, where right now when we go to a start D and we say, here's a partition slot, I have a job that I want to match here. Please create a dynamic slot that is big enough to run this job. What we're going to do instead is say, please create, let's say 2 dynamic slots that are big enough to write this job. Each dynamic slot will get its own memory and CPUs, but it should share the GPU. All right. When we do this, the access point, the SCED, will do this so that only jobs that it believes want to share a GPU will share a GPU, right? So the job's going to have to opt into this behavior. The job's going to say something like, I will share with 3 copies of myself, and the SCED will then create 4 dynamic slots that share that GPU and then run just that job on those GPUs. Also in the bag of sharing GPUs, if you have an NVIDIA A100, these can be statically partitioned into what the NVIDIA calls MIGS. These are like little GPUs that are each a fraction of the whole, but NVIDIA libraries themselves protect a job from other jobs sharing that GPU and prevent them from, say, using more memory than the MIG was assigned. This is a couple of problems with this. When we first deployed MIG support in 9.0, we discovered that almost every MIG configuration looks to Condor like heterogeneous GPUs. And at the time, we didn't have very good support for matchmaking with heterogeneous GPUs. That problem, of course, is now solved. The other problem, however, with MIGS, actually, let me go ahead and talk about that. The other problem with MIGS is it's a work in progress. There's a bunch of things that just don't work right in the NVIDIA libraries with MIGS. In particular, you cannot have more than 1 GPU at a time if you're using MIGS, right? So in the normal NVIDIA CUDA library, I can say, I want to use CUDA 1 and CUDA 2. And my job can run on both of those. But if any MIG is used on that line, then that is the only GPU you have access to. The others are just ignored. And that's not us. This is just the NVIDIA libraries doing that. Also, you have to use the long form of the GPU identifier. We're not entirely sure why, but the short form doesn't work for MIGS. And between driver 460 and driver 470, they completely changed the way that name works for the MIGS as well. So we do believe that this is a work in progress. All right, I'm going to back up a slide and go back to what I was looking at before. Here's an example of GPU discovery with MIGS. Now, this is a machine that has two A100s. One of them is in MIG mode, and the other one isn't. So we have common. The only thing that's common is the driver version. Here's the non-MIG GPU. It has the usual stuff, including 40 meg of global memory. Here's the one that was split in half. Now notice, one half is a little bigger than the other. This is what I mean about heterogeneous GPUs. This is suddenly a heterogeneous GPU, even though you split it in half. And the only configuration we ever saw that didn't have this problem was when you split it into 7 pieces. And even then, sometimes it did. All right. This is about it for me. I would like to thank the NSF for funding us and allowing us to do all these cool and clever things. And there's a few minutes for final questions.